Jai Hind to all. My name is Manoj Kumar, Assistant Professor, Department of Computer Science and Engineering, Akgec Engineering College, Ghaziabad. Today, in this video lecture, we will learn about the paging technique of memory management in operating system. So, this is the table of content that I will discuss in this video lecture. First, we will learn about the paging introduction. What is paging? And after that, paging model, then address translation in paging technique. Then what is paging hardware, what are the components of paging hardware and the working of paging hardware. After that, we will see the paging example, or we will try to understand the concept of paging with the help of an example. So first, what is paging? As we know that memory management is an important function of the operating system, and the operating system perform various activities in context to the memory management, like operating system is responsible for allocating and deallocating the memory space to a process in order to execute that particular process. Second major activity of the operating system in context to memory management is that operating system keeps the track of memory space utilized by a particular process at any instant of time. And third major activity of operating system in context to the memory management is that operating system keeps the track of overall memory, system memory utilized by the different process executing in the system, and how much memory is freely available, so that that particular available memory can be assigned or allocated to the newly arrival process. Okay, so paging is a memory management technique which is actually follow the concept of non-contiguous. It means it is a non-contiguous memory management technique. In order to allocate the memory space to the process, it is not necessary that that memory space should be available in contiguous manner. If memory space is available in non-contiguous manner, suppose a particular process suppose a particular process P, it require a memory space of 15 MB, okay, and we have a physical memory. In our physical memory, 20 MB space is available here and 30 MB space is available here, but this memory space is not available. So process P1 required 14 MB in order to store main memory, but this is also not available. But we don't have 50 MB in contiguous manner. It means we have 20 MB spaces here and 30 MB spaces here. So this available memory space is non-contiguous in nature. Still, we can load this program in main memory and we can able to execute this particular program. So this is the concept of the main memory. So paging is this is the concept of the non-contiguous memory allocation. So paging is a non-contiguous memory allocation. It means if the memory space is available in non-contiguous, then still we can load the program into main memory and execute it. Okay, so paging is a memory address scheme that permit the physical address spaces of a process to be non-contiguous. Paging avoid the external fragmentation and no need of compaction. It means basically in contiguous memory management method, the main disadvantage is of fragmentation, and fragmentation was of two types. In contiguous, like first internal fragmentation and the external fragmentation. So in order to remove the external fragmentation problem, the paging technique is used. In case of paging technique, the external fragmentation can be reduced. So this is our paging model. What we will do in paging technique? In paging technique, this is our logical memory or user program. So, and this is our physical memory or main memory. So what happen in case of paging technique, our logical memory is divided into fixed size of partition or divided into equal size of partition. Like suppose there is a memory of 16, logical memory of 16 MB, then we have divided into 4 parts and size of each parts is 4 MB. 4 MB first part, 4 MB second part, 4 MB third part, 4 MB fourth part. So the logical memory is divided into equal size of partition, and this particular partition is known as the page. Okay, partition of logical memory. The term used for the partition of logical memory here is the page. And again, this is our main memory. Main memory is also divided into equal size of part, and each part is known as the frame. Okay, here the part of main memory is known as the frame. But the condition is that when we divide the logical memory and physical memory, then condition is that page size must be equal to the frame size. Okay, if the page size is 4 MB, then frame size must also be equal to the 4 MB. Now, this page must be loaded into the frame. So, in case of paging technique, we simply divide the logical address space or logical memory in equal size of part, and each part is known as the page, and we divide the main memory or physical memory in equal size of part, and each part is known as the frame, and condition is that page size must be equal to the frame size. Now, because we have to store a particular page into a particular frame. Okay. Next, there is another data structure which is known as the page table, and basically page table itself is stored in the main memory, and this page table consists various field like consists various column, like here for example, this first one is the page number and this one is the frame number. It means which page is loaded into which frame, that information is stored in page table. Okay. So, in paging model, basically there are three components. First one is the logical memory or logical address space, second one is the physical memory or physical address space, and third one is the page table. Logical memory is divided into equal size of part, and each part is known as the page. Physical memory is divided into equal size of part, and each part is known as the frame. Condition of division is that page size is equal to the frame size. Now, we have to load this particular page into the freely available frame where it is available. It doesn't require that the frame must be available in contiguous manner. Okay. And third one is the page table is, we have to maintain a page table which consists the entry corresponding to the page number. It means which page is stored in which frame, that information is available in this page table. Okay. So, address translation scheme we will see with the help of this diagram. This is the paging hardware diagram. What happens whenever CPU want to access a particular instruction from the main memory, then CPU have to generate the logical address. CPU doesn't have any information about the physical address. So, first CPU generate the logical address, and that logical address is divided into two parts. First part is known as the page number and second part is known as the page offset. So, whenever in this, what is the role of this paging hardware? Role of this paging hardware is to find the physical address corresponding to the logical address generated by the CPU. Okay. So, whenever CPU generate a logical address, at first this logical address is divided into two parts. First part P is known as the page number, second part D is known as the page offset. Basically, page offset represent the index or logical address belongs to that particular page. For example, suppose with the help, we will see with the help of this example. Suppose this is a logical memory, size of logical memory is 16 byte and it is numbered from 0 to 15. Okay. So, we have divided this logical memory into 4 pages. This is page 0, this is page 1, this is page 2, this is page 3. In each page, 4 logical addresses are there. 0 to 3 belong to P4, P0, 4 to 7 belong to P1, logical address 8 to 11 belong to P2, and logical address 12 to 15 belong to P3. Okay. So, what happened here? Suppose a logical address is generated by the CPU is 1 and 2. So this is a valid logical address. Now we have to find the physical address corresponding to this. So in order to find the physical address corresponding to the logical address generated by the CPU, first we will check the entry of this page number inside the page table. It means in which frame this page is loaded into main memory. So whenever a logical address is generated, so first step is to check that in which frame that particular page is loaded or stored. Once we obtain the physical address for that particular frame number for that particular page, then we can easily obtain the physical address, because this value of offset in page number and frame number will be same, since the size of page is equal to the size of frame. So for example, if 4 logical address belong to this particular page, then 4 logical address must there will be the 4 physical address must belong to a particular frame. Like this is our frame. Okay, so 4 physical address belong to the frame. So value of D will be same for physical address and for logical address also, because the size of page is equal to the size of frame. If there are 4 logical address in a particular page, then there must be 4 physical address in a particular frame. So after that, once we obtain the frame number, then we can easily get the physical address. We will see with the help of an example. So let us summarize the working of this paging hardware. First, the logical address is generated by the CPU. That logical address is divided into 2 parts, page number and page offset. First, we will check that in which frame that page number is stored and where this information will be available. This information will be available in page table, and page table itself is stored in main memory. Okay, so for that information, there a register is maintained, page table base register, where we have to obtain the physical address of the page table. It means in order to access the page table, we must know about the location of page table in main memory. So once we are able to access the page table, then we can easily find that in which frame that particular page is stored. So from page table, we can easily obtain the frame number corresponding to this page number. Once the frame number is obtained, then physical address will be obtained, because the value of D will be same for logical address and physical address, since the page size is same as the frame size. Okay, so here every address generated by the CPU is divided into 2 parts. First part is the page number and second part is the page offset. Basically, page offset represent that from which logical address the CPU want to access the data. It means from which location, like for this example, if CPU want to access the C, then CPU will generate the logical address 0 and 2. If this logical address is generated by the CPU, then this is our page number and this is our page offset. It means CPU wants to access the data or instruction which is stored at this particular logical address, which is stored at the byte locations 2, like 0, 1 and 2. Okay, so here this is the concept of the page offset. Now, if there is 16 bit in a logical address, suppose logical address is of 5 bit, okay, and 3 bit is used to require the page number, then how many bits? 2 bits will be required to the page offset. This is the total length of physical address, logical address. Logical address is of 5 bits, and suppose 3 bits are required to represent the page number, then how many bits are required to represent the page offset? Will be 5 minus 3, 2. Okay, how we will see that? In this example, since the size of logical memory is 16 byte and 16 is 2 to the power 4. Okay. Now, since there are 4 pages, the size of each page is 4 byte. Here, page size equal to 4 byte. Logical memory size is 16 byte and page size is 4 byte. Since 4 is equal to 2 to the power 2, okay. So here what happened? Size of logical memory is 4 byte, 2 to the power 4. It means 4 bits are required to represent the logical address. Like first logical address will be 000, second logical address will be 001, and in the same way the last logical address will be 111. So these will be the logical addresses. Okay. Now, suppose a logical, so here the length of logical address will be 4 bit. Okay. And so in 4 bit, the size of page is 4 byte. And 4 is 2 to the power 2. It means this logical address will be divided into 2 parts. Suppose this is the logical address which consists of 4 bits. Again, we have to divide the logical address into page number and page offset. So, how many bits are required to represent the page offset? That will depends on the page size. Since here the page size is 4 byte and 4 is 2 to the power 2. So, these 2 bits required to offset D and these remaining bits required to represent the page number. Okay. So, how many bits required to the page number? That depends on the logical memory size. And how many bits are required to represent the page offset? That depends on the page size. If page size is 4 byte, then 2 bits are required to represent the page offset and remaining 2 bits required to represent the page number. Okay. How many pages are there in logical memory? 4. And 4 is equal to 2 to the power 2. So, 2 bits are required to represent the page number. Suppose if there is a size of 32 byte, logical memory is of 32 byte, okay, and we have divided into 8 pages. Now, 8 is equal to 2 to the power 3. It means in that case, since the logical memory size is 32 byte, 32 byte is the logical memory size. So, how many bits will be there in logical address? 32 is equal to 2 to the power 5. So, logical address will be of 5 bit. Okay. And if page size is 4, then 2 bits required to represent the page offset. And since we have divided into 8 pages, each page size is 4 byte, 8 is equal to 2 to the power 3. It means these 3 bits required to represent the page number. So, how many bits are required to represent the page number? That depends on the number of pages. If there are 8 pages and size of each page is 4 byte, then 8 is equal to 2 to the power 3, then 3 bits required to represent the page number, and page size is 4 byte, 4 is equal to 2 to the power 2, 2 bits are required to represent the page offset. So, let us see with the help of an example. Suppose the logical address generated by the CPU is like 1, logical address generated by the CPU is 5, sorry, page number is 1, and page offset is 3. Okay. This is the logical address generated by the CPU. Now, we have to find the physical address. So, this logical address is divided into 2 parts. First part is the page number, second part is the page offset. So, we will see first in the page table that in which frame this particular page is stored. So, page number is 1. From this page table, we can easily find that page number 1 is stored in frame number 6. This is frame 0, this is frame 1, frame 2, frame 3, frame 4, frame 5, frame 6 and frame 7. we have a here in this example we have a logical memory, physical memory of 32 byte and logical memory of 16 byte, and this physical memory is divided into 8 frame from F0 to F7, 0 to 7. This is frame page number 0, 1, 2, 3. We have stored page 0 where frame number 5. Okay, this is our page 0, P0. Frame page 1 in frame 6. This is our P1, page 1. Again page 2 in frame 1. This is our page 2 and this is our page 3. Okay. So, frame are available in non-contiguous manner and we can store the pages into the frame. Now, come to the question, if the logical address is divided into two parts, page number is 1 and the page offset value is 3, then what will be the physical address corresponding to this logical address? So, first we will see in page table where the page number 1 is stored, and from page table we have to find that page number 1 is stored in frame number 6. Okay. Now, since there are size of main memory is 32 byte, so in physical address there will be 5 bit, because 32 is again 2 की power 5. So, in physical address there will be 5 bit. 5 bit will be there in the physical address. Okay. Now, since the size of each page is 4 byte and page size equal to the frame size, so this physical address will be divided into two parts, frame number and frame offset. And since page size is equal to the frame size and page size is 4 byte, 4 is to the power 2, it means these 2 bits required to represent the frame offset and these 3 bits required to represent the frame number. So, page number is our 6 corresponding to frame number is 6 corresponding to page number 1. So, 6 is represented as 101 in 3 bit. In 3 bit 6 is represented as 101 and this is the page offset. Page offset is 3. How the 3 is represented? This value will be same 1 1. It means if the logical address is 1 and 3, or you can say that in binary it is 0 1 1 1. This will be the logical address which represents to the 7. Then physical address will be what? 1 0 1 and 1 1. And what is this? This is 16 plus 7. It means 23. So, page number 1, page offset 3. So, CPU want to access, generate the logical address 7. CPU generated the logical address 7. It means CPU want to access the H. And where the H belongs in main memory, H is stored in main memory, it means what is the physical address of H? So, see here. This is our 101 is 5110. This is 110. So, 110. Sorry. Again, see, there are how many frame number is the 6 and 6 is represented as 110 and page offset will be this. So, this will be the physical address. This will be the physical address and this will be 9. This will be 16 plus 8 plus 3. It means this will be our 27. So, if logical address is 7, then physical address will be 27. If H is stored at 7 position, then here E is stored at 24, F is stored at 25, G is stored at 26 and H is stored at 27. So, the physical address corresponding to 7 will be the 27. Okay. So, again let us see if CPU generate a logical address and like 1 and 3, frame page number is 1 and page offset is 3. So, we write it into binary. So, page number is 1, 0, 1 and 3 is this. It means logical address is 7. Now, we have to find the physical address corresponding to the 7. Now, in order to find the physical address, first we check that in which frame page number 1 is stored, and from page table we have come to know that page number 1 is stored in frame number 6. Okay, and how many bits are required to represent the frame number? 3 bit, because here how many frame are there? 8 frame, and 8 is equal to 2 to the power 3. So 6 is represented in binary 110. So this is our frame number, and value of d will be same as this d value, because page size, frame size. So d will here d frame offset will be 1 1. So our physical address will be 11011, and this is 16 plus 8 plus 3, it means 27. So if the logical address generated by the CPU is 7, then logical address is 7, then corresponding physical address will be 27. Here H is in logical memory, H is stored at logical address 7, and here in main memory H is stored at logical address 27, because at 24 E is stored, at 25 F is stored, at 26 G is stored, and H is stored at the 27. So in this way we can find the physical address corresponding to the logical address generated by the CPU with the help of the paging technique. Okay, thank you.